Hey, welcome back everybody, and hello to our online students. Today what we're going to do is we're going to have an introduction to quantum numbers. And the idea of quantum numbers sometimes strikes fear or terror into the hearts of chemistry students because it sounds very complicated. And the math behind it does require calculus, but we're not going to do that. What we're going to do is just explain what the numbers are and how we use them, not actually mathematically how to derive them. However, that is something that can be done. So what are quantum numbers? What's the deal with all of this? Well, it starts with wave mechanics. Now, wave mechanics, it's just a bunch of math that explains how electrons and other particles behave like waves. And if we remember from the last time we got together, there was the de Broglie equation that also helped to describe how objects give off certain wavelengths of light as they move. This is going to describe where these electrons are. So I think of quantum mechanics, for me anyway, is just like a zip code of where electrons are found. Now Schrodinger is this real smart dead person that came up with some of these wave mechanics and such, and he was looking at the nucleus, he was looking at a hydrogen atom. Now all of this stuff works great with a hydrogen atom. As soon as you add other electrons, multi-electron atoms, it starts getting complicated very quickly. So we're just going to look at one electron atoms. Now, the wave function itself is an actual mathematical solution for the wave equation, which is not anything that you need to derive. I'm just giving you a little bit of background here behind Schrodinger and his equation. And really what it boils down to is that subatomic particles can behave both as a wave and as a particle. Large objects like us, we don't do that. We behave like particles. We have mass. But subatomic particles, they zip between being a wave and being a particle. And that is really hard for people to wrap their heads around. And when Schrodinger proposed this, he said, well, yes, it's obvious that electrons behave both as waves and as particles. And physicists flipped out and was like, no, that's not possible. It's either one or the other. You can't have it both ways. You can't have your can't have your cake and eat it too. And the way that he described it, because not everybody could understand this, is he said, well, it's like this. Imagine if you have a cat and you put the cat in a box and you seal up the box and you want to know, is the cat alive? Well, you just kick the box, right? Kick, meow, it's alive, okay? Kick the box, thud, oh, it's dead. Easy, easy peasy. Now, what if you put a live cat in a box and then you put in like a little bowl of poison? Now, the cat may or may not eat the poison, may or may not. So you take the box, put the poison in there, put the cat in there, seal up the box, and then you say, all right, is the cat alive or dead? And you don't know. Now, if you kick the box, it spills the poison, gets it on the cat, and the cat dies. So you would have effectively killed the cat if it was alive. So the act of kicking the box changes the state that the cat is in, from alive to dead. But what if it was dead to begin with? Well, you wouldn't know. You wouldn't know. So the cat then exists as both being a dead and alive until you kick the box. Now, this is referred to as Schrodinger's cat. You may have heard of Schrodinger's cat. And people use this to explain how something could be both one thing and another. So if you're ever in a conversation and somebody asks you something, you could say, well, like Schrodinger's cat, I found him both intriguing and really annoying. And people are like, whoa, Schrodinger's cat, that's some fancy stuff there, right? Very intriguing. A more modern version of that might be the cell phone. If you take your cell phone and you drop it and it lands screen down, that screen is both broken or not broken until you look at it. Am I right? Yeah. All right, so that's Schrodinger's cat. And now we're going to take a look at these quantum numbers. Now these quantum numbers describe, so there's 4 different quantum numbers, and they describe the energy, the shape, the orientation of these orbitals and the spin of electrons. So there's 4 different things that they do. And we're going to take a look at each one of these. So there's 4 quantum numbers. 4 quantum numbers, they describe the energy, the shape, the orientation, and the spin of electrons. So our first quantum number, our principal quantum number. So I'm going to go number 1 here. Principal quantum number. Our principal quantum number, this is going to be a positive integer, and that is to say it's going to be like n is equal to 1 or 2 or 3. Okay? And this is going to tell us the energy and size of the orbital. So I'm going to say energy and size of orbital. Energy and size of orbital. And on your periodic tables, where we see this, we've seen n equals 1, 2, 3, 4 the last time we got together. On your periodic table, it'll look like this. Oh, I left out an element there. There we go. Okay. On our periodic table, we have these horizontal periods, and this here would be n is equal to 1, n is equal to 2, n is equal, do I have, yeah, n is equal to, is that right? 1, 2, yep, 3, and then n is equal to 4, n is equal to 5, and it goes all the way down to 6. I just didn't draw the lanthanide and actinide series on this one. Okay, so these, we think of these as being energy levels. So this would be the first energy level, second energy level, third, fourth, and so on. Okay. Principal quantum number. Our next quantum number is called our angular quantum number. So number 2 here, angular quantum number, our angular quantum number. And this is shown as a subscript L. And this is equal to, this is going to be equal to whole numbers between 0 and less than n. So I'm going to say 0 to n minus 1. Those are the values of it. And this is going to tell us then, this is going to tell us the shape of the orbital. It's going to tell us the shape of the orbital. Now, the shapes of the orbitals, I have some diagrams here. And maybe you've seen this when maybe you took high school chemistry and you had s orbitals and d orbitals and p orbitals. Maybe you've seen this before. So these are the different shapes of the orbitals. They're spherical and this kind of teardrop shaped, and not sure what the heck that is. That's weird. And here's kind of like dumbbell sort of shapes here. Okay, so different shapes of these orbitals. Now, if L is equal to 0, then our shape of our orbital here is going to be an s orbital. Now, S stands for something in German. This was all done by the Germans way back when. And one of the reasons that if you were a chemistry major, you had to learn German. It was a requirement at one time. But we don't do that anymore. So if L is equal to 0, that's an s orbital. Okay, that would be an s orbital like this. And where do we find these on the periodic table? On our periodic table, our s orbitals are going to be here. These first 2 groups would be our s orbital. Now, if L is equal to 1, then that would be a d orbital. And that is going to be this area here, a transition area. So like this, like that, and call that our d orbital. And if L is equal to 2, this will be our p orbital. And our p orbital is going to be down here on the end. P orbital. Okay. Any questions so far? We're just kind of going along with it? Yes. It has P as the second one. Oh, yeah, because it goes 0, S, P, D, F, G. So yeah, P comes, dang, I never studied German. I should have. I think you're correct. I think you're correct. I better change that. Okay. I'm going to blame that on my TAs for not calling that out on Professor Locken, what's this rubbish you're teaching them? Okay. Thank you for calling that out. This would have been a real mess if we tomorrow I get 100 emails and people are like, what? Okay. Oh, yeah. And still, this is still correct. This is still D, and that's still P. All right. Any other questions? S, P, D, F. Okay, all right, okay. All right, and then our next quantum number is our magnetic quantum number. So number 3 is magnetic quantum number. And our magnetic quantum number, this is M sub L. And M sub L is equal to plus or minus L. Okay, and so this tells us the orientation of an orbital. Okay, so we're going to say that this is equal to plus or minus L, and this is orientation. Of orbital. Orientation of the orbital. Okay, now we have multiple orientations, and that is to say, here is the d orbitals, right here. There's 5 of them, 5 different orientations. The p orbital has 3 different orientations, going this way, going this way, going this way. 3 different orientations. And the s orbital is a sphere. So if I try going okay, close your eyes for just a second. Okay, open it again. Right? Doesn't really matter. There's only one possible orientation for the s orbital. Okay, so now as we look at our periodic table here, how I envision this is, yes, there's only one orientation for the s, and then here in the d orbital, I've got 5 different orientations. So I like to go like this and break it into 1, 2, 3, 4, 5. See this? 1, 2, 3, 4, 5. 5 different orientations. Okay. And then the same thing happens with our p orbital. Our p orbital, there's 1, 2, 3 different orientations. 1, 2, 3 different orientations. So there's 2 boxes for each one of these orientations. And then our last quantum number is called our spin quantum number. And I'm just going to write this up here. Say number 4 is our spin quantum number. And our spin quantum number, this is m sub s. M sub s. And this is going to tell us that no 2 electrons in an orbital can have the same spin. And so this is going to be equal to plus 1/2 or minus 1/2. And what does that mean? Really what it means is the electrons are either spinning in one direction or spinning in another direction. Now, we found out that electrons actually spin on their axis, kind of like the Earth spins on its axis. And it's either spinning one way or spinning another way. And in an orbital, you can have 2 electrons, but they cannot have the same spins. So here's how I picture this in my head, anyway, is that if I have n is equal to 2, and I'm in the s orbital, I have an electron here that's spinning this way. And if I have one more electron in that orbital, it cannot spin the same way, the same direction. It will be in the downward position like this. And we think of these two electrons as being in the 2s orbital. It's in the second energy level. At second energy level, this here is our value for n. And then this one right here is going to be our shape. Okay. All right. Any questions on that? Okay. All right. Well, you folks are playing along very nicely with this. All right. So what I'm going to do next is I'm going to make a cheat sheet that puts all of these quantum numbers together. So on our table, we're going to put some columns here. We're going to put N, we're going to put L, and then we're going to put subshell letter. So our subshell letter and then we're going to put our values of M sub L. So M sub L. Okay. And then we could put our number of subshells. All right. So this is going to be our cheat sheet. And we're going to start out with n is equal to 1. N is equal to 1. So as n is equal to 1, we're in our first energy level like this. First energy level coming across. And we might think of this as hydrogen and helium over there. So L, if n is equal to 1, we look over here and we say L has to be either 0 or less than n. And if n is equal to 1 and it has to be less than n, then it would be 0. So L is equal to 0. And then our subshell letter, if L is equal to 0, then that letter is an S. Okay. So we're in our S orbital here. And then M sub L, this is equal to plus or minus L. So plus or minus 0 is 0. Okay, so that's going to be 0. And then the number of subshells. So like 1, 2, 3, 4, 5. This is 5 subshells. 1, 2, 3. This is 3 subshells. So S has how many? 1. Okay, so 1 subshell. Okay. So we're just describing then electrons that would be either here or here. So now n is equal to 2. If n is equal to 2, now we're talking second energy level. So we're talking this horizontal row here. Okay, so if n is equal to 2, then L is equal to 0, but it could also be equal to 1 because it is equal to either 0 or less than n. If n is 2, then we could be 0 or we could be 1. Our shape is going to be S or P. Let's say S or P. And then our orientations. For the S orbital, you're going to find a pattern on this. S orbital, how many orientations? 1, okay. So I'm just going to put, all right, 0 orientation there. Okay, and then, oh, wait a minute. Oh, okay, yep. All right, and then for our P orbital, our P is going to be plus or minus 1. So that's going to be minus 1, 0, or plus 1. 3 different orientations for our P orbital. 1, 2, 3. Negative 1, 0, positive 1. And we might think of it this way, right here. Negative 1, 0, positive 1. Okay? Oh, and then subshells. How many subshells in the P? It's 3. Okay. 1, 2, 3. Oh, and then this one here is a 1. Yep. Okay. Okay, because now we're going to get into the d orbital. Getting into the d orbital. Okay, so if n is equal to 3, then L is going to be equal to 0, 1, or 2. 0, 1, or 2. So that's going to be S, P, and D. S, P, D. Yes. Yeah, okay. Great question. Man, usually people like wait like days before they come back with that question. And you're just like on the spot. I love this. So the question is, how can there be a d orbital when the energy level is 2, right? 3? Right. Okay, so we're 3. We're going like here across. And you notice there's a huge absence of anything here, right? That's what you're pointing out. Yep, you are correct. And here's the weird thing that happens. Okay, so when we get to energy level 3, we're like 3 steps away from the nucleus, 3 orbits from the sun, 3rd planet from the sun. You should totally make a TV show like that. Okay, so when you get further and further apart, do you remember last time we got together, as n gets bigger, what happens to that space between? It gets smaller. Remember that? Remember that space gets smaller. And by the time we get here, the difference gets so small that they end up overlapping. And so actually what ends up happening is, yes, this is the 3rd energy level, and this right here, this first row of the D, that looks like it should be in the 4th energy level, but it's actually in the 3rd. It's actually in the 3rd. And in your textbook, you've got a table that looks like this. And as you look at this, you see the 4th energy level right here. Here's the 4th energy level. There's 4s. And then look where the D is. It's 3D. Okay, how about that? Why don't they just shift the darn things up, right? Yeah, but then it messes up all the atomic numbers. Yeah, okay. You're like, man, the periodic table is wrong. Just wait, there's more. Okay, so SPD, did that answer your question? That was a great question. I love that. Okay, so SPD, and then our values here, S is still 0, P is still -1, 0, and +1, and then D is going to be plus or minus L. So here's L is a 2, so plus or minus 2 is going to be -2, -1, 0, +1, +2. And notice there are 1, 2, 3, 4, 5 of those. 1, 2, 3, 4, 5. Oh, right? So it's almost like we go like this, right? And we go, let's see here, -2, -1, 0, +1, +2. Okay, and then subshells. Let's see, there's only 1 here. There's 3 here, and there are 5 here. All right, now I've not explained how we derive quantum numbers. I've not gone over any of the equations. I'm just showing you what they are and how they're related to each other. And we're going to use them in the next few times that we get together to identify what's happening with different electrons. Now, a test type question might look like this, where it says, which of the following combinations of quantum numbers are allowed? So you look at these. Now, this is only the first 3 quantum numbers. This doesn't have the 4th quantum number, which is the spin one. It says, which of the following combinations of quantum numbers are allowed? Hey, you, sir, with the hat. The green? Yes. You got a couple of friends there with you? help me out here. Let's take a look at the first row there, row number 1. Okay? Row number 1, we're going to take a look. Does it match our rules for quantum numbers? So, for row number 1, can n equal 1, yes or no? Is it possible for n to equal 1? Yes, yes. I didn't hear you. Yes, okay. And then if n is equal to 1, if n is equal to 1, can L be equal to 1? No, it cannot, because it has to be less than. So, oh, I guess that one doesn't work, does it? That very first one doesn't work. Nicely done. You saw through that. That'd be a great test type question. Okay. Oh, John, you've got a hat on and flannel? Yeah, fantastic. Help me out with number 2. Number 2, can n be equal to 3? Yes, it can. Yeah. 1, 2, 3. Yep, n can be equal to 3. All right, and then if n is equal to 3, can L be equal to 0? If n is equal to 3, can L be equal to 0? Yes, it can. Okay. And then if L is equal to 0, can M sub L be equal to 0? Yes, it can. Oh, it's like we have a cheat sheet here, right? Beautiful. Nobody's going to want to wear hats again. Hey, you've in the blue. Yeah, lovely. Thank you for being here today. What happens when n is higher than 3? Then we start getting into the f orbital, which is going to be the lanthanide and actinide series down here. And I try to avoid that because now we're talking rare earth elements.